Good morning, students. Today we will discuss single phase AC circuits with passive components, especially on resistance and inductance. So, let me introduce what is the meaning of the passive components. So, in the AC circuits, the voltage and current ratio is mainly depend on supply frequency and phase difference phi. It means the term impedance, which I mentioned in previous lecture also, because impedance is important component which we are when we are talking about the AC. Here resistance is the phenomena where we can say if we are talking about the DC circuit, then resistance can have some significance. But when we are talking about the AC, then impedance is used in AC circuit to denote the resistance. It means it possesses both magnitude and phase. But when we are talking about the resistance in DC circuits, then it has only magnitude there. And this impedance is represented by the Z. Resistors, capacitors, and inductors are known as the passive component. And these three components together in different combination will form RC, RL, and RCL circuits. These are also the part of our syllabus. In next lectures, we will discuss about these circuits also. So when we are talking about a resistor, then it is an element that dissipated energy mostly in the form of heat. It will have a voltage drop across it which remains fixed for the fixed value of current flowing through it. So we can say it is a property which opposes the flow of current. Okay. And the capacitor is a element which store energy in the form of electrical field, and it registered change in voltage. It means it opposes the instant change in voltage. And inductor is also similar to capacitor, but it stores energy, but that energy in the form of magnetic field. These inductors opposes the instantaneous change in current. Now let me first take a AC circuit with resistance R. What we are doing here, you can see in this circuit diagram, we are taking our sinusoidal voltage is the AC voltage V max equal to sine omega t, and that we connected a resistance here. Is it okay? You see in this circuit is the purely resistive circuit. We don't have here inductance and capacitance. It means we can call it is non-inductive circuit. It means no inductive EMF, self EMF will not present here. So the whole of applied voltage is utilized in overcoming the ohmic resistance of the circuit. It means what I can write here, this V is equal to IR. So very simple, because if we are talking about the resistance, then it is a voltage current relation which I am using here, and putting this you can calculate the value of I, and you see this I becomes equal to this one, and this is nothing but the maximum value of current. So if now I can write instantaneous value of the current here, it means I equal I max sine omega t, or I max is nothing but V max upon R. You can see here the phase difference is 0 here, and in previous slide you can see phase difference 0 here. It means when I draw the wave forms for the current and voltage, you can see this waveform is for voltage and this waveform for the current. Both are in phase at every instant, both are the in phase. Only the magnitude of current is lower than the magnitude of voltage by the factor 1 by R only. Okay, and if you see the phasor diagram, then in this condition both are same. If I am taking point this here, here the theta angle is same here. Okay, and if I am taking theta is angle is here, so you can see here everywhere the both quantities are in the phase. You can see clearly here it's the maximum of voltage, it's maximum of the current. So everywhere the phase is same. So in the phasor diagram you can represent it by like this way, or you can represent it by this way. If voltage in this direction, current is direction. If voltage is rotating like this way, current is also rotating in this way. Let us suppose voltage here this one, it means current is also here, only the magnitude is lower by the value of 1 by R. Is it okay? So it means there is no phase difference between current and voltage when we are talking about the purely resistive AC circuit. Okay, so it means what we can say, in the resistive circuit the applied voltage and current are in phase to each other. Now, if I want to calculate the impedance of pure resistive circuit, then how I can calculate? This is nothing but the voltage, applied voltage divided by the current here, and you see the phasor form of the voltage is this, and phasor form of the current is this. So it is nothing but because Vm divided by the Vm upon R, so it becomes equal to R. So what I can say here, the resistive impedance, or we can say the impedance of pure resistive circuit is equal to R plus J0. It means the impedance of pure resistive is equal to only the resistance. It means is it equal to its DC resistance only. There is no complex part in the impedance of pure resistive. Is it okay? Now we will calculate the power of purely resistive circuit, and we will see what is the value of this. So the power is nothing but it is the product of the instantaneous value of the applied voltage and current. We will see here, we calculate the value. Power is nothing but voltage and current, put the values, and sine square is nothing but sine square equal to this. So put this value, put this and this here. Now take the average value for whole cycle. It means I am talking about the complete cycle, this one, 0 to 2 pi. So if I are to taking the average of this value and this value, so this value, because it's the 2 omega t double frequency of our complete circuit, its value becomes equal to 0. So this is equal to this, and V max upon root 2 and I max upon root 2 is nothing but is the RMS value of voltage, and it is the RMS value of current. So this is the power in pure resistive circuits. So what we can say, that the power consumed in pure resistive circuit is not constant. You can see it is not constant, but it is fluctuating. You see this one it is fluctuating like this way. Okay, why it is fluctuating? Because the sine square terms comes here. I'm talking about here instantaneous value of the power. That power is fluctuating here. When I'm taking the average of that, then you can see the average value of this one is the average value. It is the average value of this one is the average value. Is it clear? And it is the maximum value of power here. And here you can say the power is always positive because current and voltage both are in phase everywhere. So whether we are talking about the positive half cycle, or if we are talking about the negative half cycle, both are in the same phase. So everywhere our current is always positive in the pure resistive AC circuit. And what is the meaning of this? This means that the voltage source continuously delivers power to the circuit and the circuit consume it. It is the meaning of this. Okay. Now we have the AC circuit with inductance. Again, what we are doing here, we are applying our alternating voltage V equal to V max sine omega t to pure inductive coil. And here we have the inductive coil. It means this coil have here self inductance, and due to this we have here self induced EMF in this coil, and which opposes the applied voltage is the according to law of the Lenz law. Since coil has no resistance, at every instant applied voltage has to overcome this self-induced EMF only. Is it clear? So let us suppose we have to calculate the value of induced EMF here. So it is our applied voltage, and then self inductance is defined by this. So the self induced EMF will return the self inductance multiplied by the change of current, because I already told you the inductance, or we can say the inductors opposes the instantaneous change of the current. So that's why I'm putting this value here. Is it okay? And the applied voltage will oppose to self-induced EMF, so that's equal to is minus. So I will put minus here and minus here, so this value becomes equal to this one here. Is it okay? Di omega is becomes equal to this current is here. So if I integrate from the both side, then what I will get, this one is minus cos omega t constant. If you put the initial values, then this constant becomes equal to 0, and this becomes equal to minus v max upon omega l cos omega t. So this is nothing but it is the sine omega t minus pi by 2. Because of this minus, we put like this way. And from this, how you can write? You can write the I equal to I max sine omega t minus pi by 2. And this minus pi by 2 is the phase angle in our instantaneous current. So this I am representing here like this way. Is it okay? Or I max is nothing but V max upon omega L. So what we can see here, see from these two terms, first one is this, or you can see this. Here is the phase angle is 0, but here you see the phase angle is minus 90. It means current lagging by the 90 degree, or you can see the pi by 2. So that I will represent in the next slide. So this is our circuit diagram. We are applying our alternating voltage on a inductor coil here, and you see here what we have, it is our voltage. See, this is the our voltage, and the current is behind by the pi by 2. So current is lagging here. Is it okay? So current is lagging here, so that I want to show here. In the inductive circuit, the current is lagging by the pi by 2, and that I am representing in a phasor diagram also. This is my voltage and it is current, so this is lagging by pi by 2. So that's the phasor diagram, circuit diagram, and it is nothing but the sinusoidal waveform diagram to represent our current and voltage, as well as power also. We will discuss in the next slide. So here we can define the inductive reactance also. If you see in the previous slide, from this, I can define WL equal to Vm upon Im. From this I can define here WL in the expression from this is known as the inductive reactance, and it is denoted by XL. So XL is nothing but omega L, and omega L is nothing but inductive reactance. Its unit is the ohm here. It's also the resistance, and it measures the opposition to the change in the AC current through the inductor. That is the what is the physical significance? It is measures the opposition to the changes in the AC current through inductor. That is the meaning of this. Let me calculate here the impedance of pure, also it's a sorry, pure inductive circuit. It's not resistive, but it is inductive circuit. Is it okay? So if I put this value and this, you can see it's a minus pi by 2, so it's divided by minus pi by 2, so it's become pi by 2 here. And I can write this one, this and this here, or we can write this like this way. It means we don't have real part here, we have only the imaginary part, and imaginary part is related to here the inductive reactance omega. So you can see the inductive impedance, the resistive part is 0 and inductive reactance is omega L. Now we will calculate the power in purely resistive circuits. So we put again this value and then solve. We open this because it is sine omega t and pi by 2, so you will write sine omega t and cos pi by 2, so that term becomes equal to 0, and then minus cos omega t and sine pi by 2, so sine pi by 2 is equal to 1, so this term becomes equal to minus this one, this, and this becomes from this, and that we can write here using 1 upon 2 sine 2 omega t. And if again I will take the average of this, then for a complete cycle it becomes equal to 0. Is it okay? So this becomes equal to 0. So since the average of sinusoidal quantity on double frequency over, why we are saying, because we have 2 omega here, complete cycle is 0, hence a pure inductive circuit power absorbed is 0. And what is the physical significance and how we can explain physically the uh, power is absorbed power is 0 in inductive circuit. So we will see in the next slide. So see here, it's a very conceptual thing. Physical explanation to P equal to 0 in pure inductive circuit. You see from this wave diagram, current is moving this, it's okay. So here current is negative, but if I am talking about the second quarter, it means I am talking about this from pi by 2 pi. In that condition you can see the current is increasing, you can see here, okay. So in second quarter, the current, or we can say the magnetic flux of the coil increases, and in this condition what is happening, the coil draws power from the supply source to build up the magnetic field, okay. It means the power drawn by the coil from the supply source we are considering positive, and the curve lies above the time axis. So you can see I'm talking about this one is my positive power, so we are talking about the positive. So in this case, when current increases or magnetic flux is increases, and that condition, the coil draws power from the supply source to build up the magnetic field here. Is it okay? And that is stored in terms of the magnetic energy, and that is nothing but half inductance and I square maximum. That is the magnetic energy stored, okay. You can see in this diagram in the next quarter, it means I am talking from pi to 3 pi by 2. In this quarter you can say the current is decreases. Is it okay? So the EMF of self-induced will tend to oppose this, its decrease, because it will be decrease as per it will be oppose its decrease as per the Lenz's law. So the coil acts as a generator of electrical energy and returning the stored energy, which is stored as a magnetic energy. Now it is returning the stored energy in the magnetic field to the power supply, and that is we are representing by the negative, and it is lies below the time axis. So you can see in this here, this one, in this case what is happening, the current is going like this way, this one. So in this case The coil is drawing current from the power source, and in this case the stored magnetic field is returned back to source. That is the concept behind it. So it's the half cycle of the current. It's okay. This one is the pi by 2 to 3 pi by 2, you see. But in the first quarter, the power is drawn by the coil from the source, and in the second way from pi by 2 to, oh sorry, pi to 3 pi by 2, in this case you can see the power is the stored magnetic energy is returned back to supply. That is the meaning here. Is it okay? So this chain of event repeats itself during the next half cycle also. Thus, the portion of power is continuously exchanged between the field and inductive circuit, and the power consumed by the purely inductive coil is zero. That is the meaning of this. So today we have discussed about purely resistive circuit and purely inductive circuit. In the next class we will discuss about the purely capacitive circuit and then their combinations. So I think you understood the concepts behind the waveform, then the power, and then the current is lagging and voltage is lagging, and how the phasor diagram is represented here, and how the power is calculated, and what is the role of power. Everything we have discussed here, and you, I think you are able to understand this. Okay, if you have any problem, then you may write on charm at the red gwec.ac.in. Thank you.